Okay, we will restart. I don't know if it was me or I saw we were just with 5 people. Someone I don't know has joined. I don't know who it is, but yeah. Okay, we'll see. Where were we? Okay, yeah, we can do an example. So hypothesis testing, remember there were 2 ways to do it. So you can use the critical value method or you can use the p-value, and you should get the same answer. Sometimes it says use p-value, sometimes it says critical value, sometimes you can decide yourself. Okay, so what do we want to test? Yeah, from the ANOVA table, we see that n minus 2 is 82. Under residual degrees of freedom, we already said that. So let's have a look. Where is she? Here's our ANOVA table. So on the residual and df, so that's 82. And yeah, we knew that already. And we had those coefficients, remember? Those 2 coefficients. Yeah. Okay, so we want to test something. We want to test if beta 1, so the true regression slope coefficient, is less than 2000. So the B1, so the estimator of the true coefficient, was this, so the 1700. You can see my screen, right? Yeah, I think so. Okay, and we want to test if that's really truly more than 2000. Yeah, that's what we want to test. I didn't include, okay, I should have included it, but the critical, the alpha is 0.05, so 5% confidence. Okay, first step is write down our hypothesis. So we want to test whether beta 1 is less than 2000. So the default, this is our alternative hypothesis, and the other hypothesis is whether beta 1 is more or equal to 2000. That's the opposite. It's always the opposite, and you always include the stripe, like the equal, in the null hypothesis. Okay, that's step 1. Step 2 is the test statistic. So the test statistic, here it's a t-test because you want to test only one thing. So it's a t-test, and you just write down the formula and you fill in the hinge, so the 2000 under T82, because that's our degrees of freedom, but I usually don't include it. And then you get the value of the test statistic. We can actually calculate it ourselves, so we will do that. You get this number, you click it a few times, and then you get it like this, and you copy it, you put it in Excel. And you subtract 2000 from it because that was the hinge, and you divide it by this number. Control copy. Put it in there, and you get an answer. So this is our t-value, right? Okay. I think, yeah, that's the same answer. Then you can calculate either the critical value or the p-value. So let's start with the critical value. This is a lower-sided test, so a lowercase test. And remember that we want, for the critical value, you use t.inf. Now I should put the is in front of it, otherwise it doesn't work. And you always put it between brackets. Oh, it says probability. Okay, what was our probability? It's always to the left. We said that already. So if you have this curve, Excel always calculates what you put to the left of it. So if we put 0.05, and the degrees of freedom, which was 82. And our critical value is this. You can also do it, which is the same, t.inf. You can also say 0.95 and then 82, but you have to take the reciprocal. So you have to put the minus in front of it yourself. Because what it does now, if you have the curve here, here's the curve, so, and here, like about here, that's what you calculate now. Like this is your curve, and this is where you are now. So it calculates this entire area. But we want this part, what's on the other side, because we take the reciprocal, remember? So you just put a minus in front of it because it's a lowercase test. So you get the same answer. Sorry. You get the same answer, but you have to put a minus in front. No. Yeah, sorry. You have to put a minus in front of it if you do it like that. So you just take like the opposite, because you know it has to be negative because it's a lower tilt test. That's for the critical value. Let's now do the p-value, and then you take t.dist. Here's our t.dist, and it asks for the x value. And the x value is your value of your t. And we had calculated this above. So you just take it. Then it asks for the degrees of freedom, which is 82 again. What I put here, by the way, so this x, that's, remember, it's the probability that you get this, so the p-value is the probability that you get the outcome as extreme as your t-value, which was minus 2.30593. And that's like your little x value. So you put that there, and you take 982, and it asks cumulative. And then you just put in true, because you want the cumulative. You want everything that's below the curve. And if you would put false, you would get, if you remember from statistics 1, you would get, you get something else. You get like, now you get an area, and then you get sort of a stripe, I think. But that's not even possible because it's a continuous thing. And this would be our p-value, I think. Let's see if we have it correct. Yes. So this would be our critical value. We had calculated it as well. I had 1.663 and a minus, but you round it to 1.664. Okay, and our p-value is this one, so that's 0.012, which is also the same as this one. So our critical value is minus 1.664. Remember that to reject it, the value, our actual value, is smaller than the critical value. And the critical value is the value at which you may reject H0. And anything smaller or bigger than that, so if you have a positive critical value, anything bigger than that allows you to reject it. And if you have a negative critical value, anything smaller than it allows you to reject it. Because remember, we had this curve, and then if this is our critical value, and I get a value here, then I may reject it. We get a question. Bram. Who is Bram? Could you please, like, are you following this? Because I didn't get an email that you subscribed for this, but okay, we'll continue. We'll wait for his answer. So if the critical value is this one, and you get a value that's here, then you can reject the null hypothesis. And if you have a positive critical value like this, and you get a value here for your t, then you can also reject it. So, like I said, it's smaller, our actual value is smaller than our critical value, so we can reject H0. Do we get the same for the p-value? Yes, because our p was 0.012 and our alpha, I didn't include it, but it was 0.05. Obviously, this is smaller. And so you reject H0. There is evidence that p1 is less than 200 because you reject this, so you tentatively accept this one. Okay? Okay. So this slide explains what I have just done, basically. So for the critical values, you always use t.inf, and for p-values, you use t.dist. For an upper tilde test, you use 1 minus this one, because as I said, you want the p-value, you want this area, but Excel always calculates this area because it always works to the right. So you do, sorry, wrong slide. So you do 1 minus that, and for a lower tilde test, you just want this. Oh, that's already to the left, so you don't need to do 1 minus it. And for a two-sided test, that's important to know, you use this one. T.dist does to t. If you want, you can make a picture of this, but it's also in the slides. Yeah, so that's what you use, and then you can also use one of those, by the way, but it's going to be more difficult because then you still have to divide it by, still have to do it times 2, and this one does that for you already, because with a two-sided test, a lower-sided or upper-sided only calculates one of those, and with a two-sided test, you want both of those, so you have to multiply it. Right? So yeah, that's basically it. Learn this slide, and yeah, you just have to practice this. Also, if you have alpha is 0.05, you take like sort of the reciprocal in Excel, because so this is 0.05, but you calculate this, right? So you take 0.95 because Excel wants 0.95 and not this one. So you have to subtract that yourself. But that's just common knowledge that you will need to learn, and I can't really explain it. It's very clear on this slide, I think. Okay, the most common hypothesis test is a two-sided test when the hinge is 0. And that's, for example, beta 1 is 0 versus beta 1 is not 0. Remember, this is the format of a two-sided test with a hinge 0. And under H0, the model is useless. Why? Because the value of y doesn't change for x. If beta 1 is 0, then if x is 100, then y still doesn't change, because 0.0 times 100 is still 0, right? So then the model is useless, because the model is actually equal to b0, which is a constant. So it's a constant straight line. Under H1, so when beta 1 is not equal to 0, then the model is useful, at least to some degree, because then the expected value of y given x is beta 0 plus beta 1 times x, and beta 1 is not 0 in this case. So if x changes, y will also change, and then it's useful. So if H0 is rejected, so we tentatively accept H1, then we say that variable x is significant and b1 is significantly different from 0, which means that it has an influence on y. And if H0 is not rejected, then so beta 1 is 0, we say that variable x is insignificant, so doesn't make a difference. And beta b1 is not significantly different from 0. So the difference is that if this is accepted, then the model is actually useless because it's not significant, or this variable won't be significant. I see a lot of chat, so let me quickly open it. Oh, you got invited? Okay. I'm really sorry. Did you subscribe for this crash course of statistics? If you want, you can also unmute, because like I also got an email that I subscribed for another crash course, which I didn't because I just passed the course. So I know it happens sometimes and it is really annoying. So if you can let me know, then we'll figure it out. Anyways, yeah, so that's a test that you will see very often. And it's actually the simplest test because SPSS gives your t statistic by default. What do I mean with that? If we go to SPSS, here it is, and you see the t here. This t can only be used if your hinge is 0, because what it is actually this one divided by this one, and you get this number. You get 13. But if your hinge, for example, is 2000, like we just had, then it won't be this number, because this minus 2000 is minus 300 something divided by this is obviously not this. But if it is 0, then you get your t, so your value, you get it here already. And that's really useful because you don't have to calculate it yourself. I see the chat. Okay, you did subscribe. No, you don't actually get the PowerPoint, but because I had internet problems myself, I didn't, by the way, get an email that you subscribed. So I also don't know how you got this link. If you want, you can of course join, but I mean, but my internet went out, so I think that's a good excuse for me to send you the PowerPoint, yes. If that answers your question. Let's continue. So under the ANOVA table, the significance test can tell us if a model is useless or useful, but we want to quantify the usefulness of the model. Because if beta 1 is not 0, I said on the previous slide, okay, we say it's useful. But how useful is it? Sorry. We can do this by comparing the error before and after regression. So without a regression, we predict the value of y using the sample mean, because really we don't have anything else to do so. And the total sum of squares, this should be sum, another mistake. The total sum of squares, SST is what we call it, where I see the t as total, that's how I remember it, is then the actual y minus the predicted value of y squared. That's the SST. I'll get to a picture soon so that you can get it, get the idea. And with a regression, we predict y by using the predicted value of y using that formula, remember? And then the sum of squared errors, which we call SSE, also easy because error and e, is the y minus the predicted value of y squared. And it's squared, and here it's also squared. So that's why you see those twos. And that is then our sum of squared errors. Because with the regression, we actually have this predicted value, which we don't without a regression. And then you will use the sample mean y stripe. Okay, let me put this in a picture for you. So SST, remember, that was the sum of squared total. which is the squared deviations from the sample mean y stripe. So that is this purple-ish line. And you see, that's quite a deviation, right? Because this black line is the sample mean, and yeah, that's quite a deviation. Some points are closer, but those are really far away. And then your SSE, that was what we use with regression. So that is the actual point and the difference with the line. Remember, we did that already. This is your error or residual squared. Yeah, residual in this case. And that's why they also call it the squared errors, because we saw already that this was your error term, right? This is your error. It's blue line. It's a difference between your point and the line. It can be positive, it can be negative. Okay, but we have this part, and what is this small part then? We call that the SSR. And the SSR is the difference, here you can see it, is the difference between your prediction and the mean. Prediction, which is here on the line, and the mean. Again, it could be negative if your line is here and if your prediction is here and your mean is here, then of course it's negative. All right, so that is what we call your SSR. So that's this small part. And what is your SSR? It measures the variation that's explained by the regression model. So this was your entire variation. This is the model variation that's left if you model it, because we can't explain this variation. But this part is now gone, and that's the SSR. And it stands for sum of squares due to regression. So yeah, that's of course logic, because regression, SSR, R stands for regression. And that's what we sort of cancel out due to having this regression. And then, like I said here, so if this is our SST, this is our SSE, and here we have our SSR, then our SSR plus our SSE must be our SST. And that's the relation that we see here. So our SST is our SSE plus our SSR. Okay? Okay. Then we get the coefficient of determination. Which is also called R squared. And what is our R squared? Our R squared is the SSR divided by our SST. So it's the variation that's explained by our model, SSR, divided by SST, which was the variation in total. And it's actually the same, of course, as 1 minus SSE divided by SST, because SSE plus SSR was SST. And a small fact, for the simple linear regression, and only for the simple linear regression, this is the same as the square of the sample correlation coefficient. So R squared is the same as small r xy squared, but you don't need that. No. And the R squared is always between 0 and 1. That is because SSR and SSE together are SST. So SSR is a part of SST. So if the model doesn't explain any variation, it will be 0. If the model explains all the variation, it will be 1, and otherwise it will be something in between. So if R squared is small, then the model only explains a small amount of the variation in Y data. And if it's very large, then the model explains a lot of the variation in Y data. That's, I think if you understand the formula, that's intuitively clear. For example, if R squared is 0.75, or if it's 0.50, for example, then the model explains 75% or 50% of the variation in the Y data. So 3/4 of the variation in the original data is now explained by modeling, and 25% is left unexplained. Okay? Okay. We only have 2 slides for this PowerPoint. Okay, great. We go to the ANOVA table because there we can find our R squared and some other important things. Yeah, sorry. You can calculate the R squared yourself. So what you do is you take here's the sum of squares for the regression, for your residual and total. So this is your SST. This is your SSE from residual or your error term. Here we use residual because we have, of course, a sample, but as I explained, the error and the residual are, of course, like the same, only you have a sample for the residual and a population for the error. So this is your SSE from residual, and this is your SSR from regression. So what's your R squared? It's simply this number, your SSR, over your SST. All right, and that's in the ANOVA table where you can also find the degrees of freedom. Then, yeah, here you can see it a bit more clearer. So this is your SSR, your SSE, your SST. All right, I think that's, yeah, and this can also be used. I already explained this one. So your SE squared is this one over that one. Remember, we looked at this already, and then you get this number in the middle. But you don't really ever need it. No, you only need your SB1, and that's this number divided by something else, and that number you can find in your coefficients table. Okay, if there are no further questions, I see no chat. Okay, Bram is still here. I think you subscribed then. Feel free to follow. Last slide from this chapter. Prediction intervals. We have confidence intervals and a prediction interval. We already discussed the confidence interval, but it's different from a prediction interval. What is exactly the difference? Let me explain it. So we can use our model to predict y for any given x. So if we have this model, and I say my x is 80, what do I think my y value will be? Well, it will probably be somewhere like 185, right? Okay, so we can predict that with our model. But we are not sure how close we actually are, and that depends on our prediction errors. And yeah, the standard errors for these estimators are different because we use our predicted y to predict, of course, y. Yeah, we use our model to predict y, sorry. And but this predicted y might actually not be the actual y. And we have to see how close it will capture the actual y. And we can do that with two sorts of intervals. We can do it with a confidence interval and a prediction interval. And the confidence interval, it estimates the expected value of y. So for example, if I have a population, and I take a sample, and I want to know the age of the population, the average age, right? Then I can use I can use a confidence interval to predict with how much certainty we get close to that actual, how much certainty we have to actually include the actual mean value. So I have 95% confidence to include the actual mean, and I say the mean is, for example, between, would it be 30 and 45, for example. Okay, I think that makes sense, right? Because of course the mean is probably, would it be 40 or something? I think, yeah, I would say 40. So 30 and 45 captures that probably with 95% confidence. What is then the difference with a prediction interval? Well, a prediction interval contains the actual realization of YP. And that's where I think it gets difficult, because you have the mean of YP and the actual value of YP. So if I want a prediction interval and I take one person from the population, I must have 95% confidence to have included his age in our confidence interval. So above it was about the mean, and here it's about one specific person. So of course, one specific person can range from, 0 to maybe 110. Probably most people won't get 110, so yeah, you can leave a lot out. So probably the interval will be the age of 1 to 80. So you already see that interval is a lot bigger. And that's also what usually happens. The interval for the prediction interval will usually be a lot bigger, because you have to estimate it for one specific person. And here you have to only estimate it for a average. So I hope you understand this. If you don't, you can ask me again, because it is a bit complicated, I would say. Let's do this in SPSS. Okay, I still have those. I'm just going to delete those because I don't need them. Yeah, now they're gone. Okay, you scroll down and say, what do we want? Scroll to the end. Okay. I want to, if my sale price is 4, I want to know my predicted value, because remember, sale price was our X, so our independent variable. I want to know the daily units sold, or what my model predicts. And we can actually do that with SPSS. But remember to leave those blank, because if you don't, then SPSS won't calculate it for you, obviously. So you go to Analyze, you go to Regression again, Linear, because we only do linear. Oh, this is still there, so that's great. Let's see if I want to untick this, because otherwise I get all those and I don't need them. I have daily gross sales and our sale price now. Okay, and now I go to plot. No, I go to save. Yes. Do I want my residuals? No, I don't need them. I do want my predicted values, because I want to predict what my y would be under this 4, given my line. And I also want prediction intervals, and I want it for my mean, and I want it for my individual. So your mean is your confidence interval. Remember, that was for the mean of a population. And your individual was for one person. So that's your prediction interval. And I wanted it at a confidence of, let's see, 95. Okay, so that's again the default. And you click on continue. Going to have to move this again. And you click on OK. Right. So you get this output, which you don't need, because you need this output. Here you get pre-1. So that's my prediction. So I predict that for a sale price of $4, I think, yes, my daily, what was it? Is a prediction interval for, let me see, sorry. I don't know if it was. One second. It was a prediction interval for our daily gross sales. Okay, so you predict that at the value of 4 sale price, our daily gross sales will be 7,793.043. Okay, so that is our prediction. But this prediction must be between an interval. And here I get 4 outputs. Okay, and the L stands for lower bound. It also says it. If you just click it, it says, again, now, yeah, here it goes, 95% LCY. So that's lower, CY stands for confidence interval. And this is U, and U stands for upper, lower, upper confidence interval, again, CY. So this is your lower bound of your confidence interval. Remember, your confidence interval was for a mean value. So the confidence interval is this value. So with 95% confidence, your mean population value is between this. But with 95% confidence, your this is again L and U, so lower and upper, and this is Y again. That's weird. This is to be your prediction interval. This is your prediction interval. So with 95% confidence, your predicted value is between those two values. Why do I know that? How do I know that this is my prediction interval and not my confidence? Because like I said, your prediction interval is always a lot bigger. And obviously you can see that this interval, which is between minus 480 and 16,000, is a lot bigger than 600,000 and or 6,000 and 8,000, right? Let's see if we have correct. Yeah. Okay. Are there any questions about these slides? I'll give you a few minutes to process, and if there are any questions, you can. Okay, so I assume there are no questions. If you do get a question or anything, you can still ask me. There's still some time, and we will now start on the second slide set. So these were chapter 5 and 19. I'll open. Oh, I see a chat. Yeah, you can ask a practical question. Okay. Yeah. Like I said, I'm actually not allowed to send it to you. They do look a lot like the PowerPoints on Canvas. I sort of got most information from it, but like I said, my internet went out. So oh yeah, okay, yeah. Then that's probably a very good excuse to send it to you guys. Yeah. So I'll get it to you. Okay. Then a second PowerPoint. In this PowerPoint, we will discuss chapter 20, 21, and 22. We won't finish it entirely today, of course. That was my intention, but yeah, we also lost some time due to my problems, and we don't need to. We can easily finish all that I wanted to discuss in today. And the last lecture, or the last crash course day, which I think is Wednesday. So we will just start on it and then see how much we can do today. See some questions? Oh, you can just type your email address. And one small question: where did you get this link from Zoom from? Because someone must have shared it with you, but I don't know who did. Because I didn't have your name. But that doesn't really matter. As long as you subscribed, I think it's fine. Canva sent you this. Well, that's weird. Yeah, that's weird. Oh, okay. Okay, that's weird. Yeah, because I first organized like a conference, but then one student wasn't in our course, so we had to do it differently. That's why we're on Zoom now. But okay, anyway, we'll move on. Okay, so chapter 20, 21, and 22. Crash courses. Oh, okay. No, it's fine. It's fine. Yeah, we will continue. Okay, so before we talked about simple regression analysis, right? And then we had just one variable, so one x. So for example, the demand depends on the sale price. But it could also be that demand depends on the week or the day or on the time, so in the morning or in the evening. So it could depend on more things. And that's why we now introduce multiple linear regression, which suggests that something can depend on more than one variable or more than one item. And yeah, we model this. Actually, it's very much the same. So we still have this beta 0, which is our intercept. We have this beta 1, which we had before. But now we also have a beta 2 up until beta k. For example, k can be 20, it can be 3, it can be 100 if you want to. And we also have our error term, because the actual y is predicted by the line, but the actual y is the line prediction plus the error. And much of what we learned from this simple linear regression carries directly over to this model. Yeah. So the assumptions of the multiple linear regression model are the same. So that's easy to remember. If you know the assumptions for a simple regression model, you also know them for multiple linear regression. Yeah, so remember we had this line, y is beta 0 plus up until including beta k xk plus your error term. An expected value of your error term given x 1 until xk is 0. For all values x1 until xk. Because the first assumption was linearity, where we assumed that the error term, or the average of the error term, the mean, is 0. So our predicted value of y, or our value of y, is predicted by this line, right? That was the basic assumption, or linearity. And another way of writing that was the expected value of y given x is just the line, because the expected value of the error is 0. So normally there is this e term, but that's 0 now. Okay, that was the first assumption. Then we had the second assumption of homoscedasticity, which meant that the variance was like constant. So at small values of x, there would be some dispersion in the error terms, which would be the same at larger values. Thus not that at small values of x, the sort of dispersion is small, and at higher values it's very large. No, that would be called heteroscedasticity. So now we have linearity and homoscedasticity, and those are actually, like, I think this is a bit strange to be written down, but they include those assumptions because we have 4, right? We only see 3 bullet points here, but the assumption of homoscedasticity is included here, in fact, because this is a constant variance, which we set to be like this. And the mean value was 0, because we said that here. Here, the mean value of the error is 0. So then the normality assumption is the error term given the axis is normally distributed with a mean of 0 and the variance of d sigma e squared. And conditional on these, the errors are normally distributed. So that's the normality assumption. Then we have n observations, so xy1, xy2, xyk, and or y values, and they form a random sample. That was our fourth assumption, which was independence. So we have 4 assumptions. First, linearity. Second, homoscedasticity. Third, normality. And 5, independence. Okay? And so actually the assumptions are the same, only with more terms. And then we have the interpretation of the coefficients. B1 is now how much the expected value of y increases when x1 increases by 1 unit and all other variables remain unchanged. Okay? So the expected value of y, so that's you could also say on average, or expectedly, or the expected value of y. But it is when all the other variables remain unchanged. And that is the same as ceteris paribus. I always say ceteris paribus, but you can also say unchanged, remain the same. It's all equally. And in red, so for Bram, I think, let me see, yeah, Bram, everything that's really important, I have made it red so that you won't miss out on it. So what we say is when x increases by 1 unit, all else equal, or ceteris paribus, y changed by beta 1 on average, or expectedly. So average is mean, is expectedly, or the expected value of y. And instead of saying all else equal, we sometimes say ceteris paribus. But there are always 2 very important points to include, and those are, I've made them bold. So all else equal. So I can change x1, but then the rest must stay unchanged for y to increase with beta 1. because I can change x1, but if, for example, x2 changes as well, then y doesn't change with beta 1. It might change with beta 1 and more. Or it changes by beta 1 and less if the other coefficient is, of course, negative. And you also have to include on average. Why on average? Because the line is an estimation. As we said, there are errors. It might be wrong. But on average, it would change with beta 1. So always include those two things. After estimation, we obtain the sample regression line y hat is b0 plus b1 xy1 plus bk xy1k, where yi hat are the predicted values, and ey are the residuals. They didn't include them here because this is the predicted value, and to get the actual value, you do the predicted plus your error. That's why they didn't include it. But sometimes, like, this looks very complicated, I think. And often they just leave out the y. So what does the y actually mean? So if you have multiple points, so I, for example, 3, and then you get, for example, 6, and I have 4, and you get, for example, 7 or something, I don't know. Then the y stands for those multiple values of 1x. So yeah, I don't know if you see what I mean, but I mean, first I have the x of 3, I can fill them in everywhere. And then I have an x of 4, I can fill them everywhere. And that's where the y stands for. So it stands for multiple, multiple tries actually. And then eventually you get one line. You should be able to, you get those points on that line. Okay, I hope that's clear a bit. The interpretation of the coefficients is the same. Only you must say all else equal, because now you have more coefficients. And with the simple regression, you only had like the beta 0 and the beta 1, and the beta 0 was constant. So actually you had only one real coefficient, I would say. And now you have more. So it's only right if the rest stays the same. Okay, let's do an example in SPSS. We're going to need a new file. If you want, you can open it with me. I think it's in week 3. Yeah. Which one was it? XMP 2001. Yeah, it's this one. I'll get rid of the old ones. Okay, there it is. Okay, so we have a few variables. The W, which stands for wage, I think. Yeah, it isn't included here, but I know it stands for wage. We have H, of course, and ED-WAL, which is education level. Okay. And it says we have 150 people. Okay, so our N is 150. And to estimate this model with the YH and X1 wage, and X1 age and X2 education level, we have to do the following. It's actually very much the same as the simple regression, as the simple linear regression. But the only difference is that if I put wage here, I have to put age, of course, in the independent because the dependent is the wage, which of course depends on age. Usually if people get older, they also get a higher wage. And if they have higher education, usually they also get a higher wage. So I put those in the independent because they are the independent variables that on which the wage depends. So that's the dependent variable. And furthermore, we don't have to do anything. So I'm going to click on OK. And we get an output. And here, where we first saw only a constant and then one variable, we get two variables. Here again are our coefficients. Here's our standard error. Here's our degrees of freedom. Here we already see something weird because we had an n of 150, right? So that was our sample. But our degrees of freedom isn't 150 minus 2, like it used to be. It's 174. So it must have been n minus 3. And we will get back to that later. I think I already explained it for the ones that were there at the beginning. You might already know why, but we will come to it. We can also test the model assumptions in SPSS. Yeah, we already made the model like we just did. But again, for the model assumptions, what did we want to test? We wanted to test whether the residual, so whether it was the linearity assumption, the homoscedasticity, the independence, and the normality. So we wanted to test if the error term, if it was 0 on average, if its variance was normal, if its variance was constant, and if the error terms were independent. That were our assumptions. We already did that for a model with only one simple regression model. And now we want to do it for a model with several variables. So if we want to do it, we go to our model, you go to Analyze and Regression again, Linear. We still have the model, so that's nice. I'm going to tick Save. And I will click Residuals. That was obvious, because we want to check the residuals, if they're independent, if they have how their variance is and how their mean is and stuff. So we definitely need the residuals. We also need the predicted values, and I will explain that later. So you click Continue. And you click on OK. Okay, we get a graph here. And we get our predicted values and our residuals. What are we going to do to test them? To test the first assumption, that one of linearity, we go, the thing is, I know it's really inconvenient, but with linearity, you have to check it for each variable. And that's annoying, I know, but there is no other way. So remember that for linearity, we made this graph where we plotted the residuals against the x value, because that's when we can see if the average is 0. So you go to Legacy Dialogues. Again, scatter dot, simple scatter, define. And then you take wage. No, sorry, that's wrong. You take the x value, so that were age and education. You can only take 1. So you put that on your x again. And you put your residuals, your unstandardized residuals, on your y-axis. Click on OK. and you get this graph. Remember, linearity was the assumption that at each value of x, the residuals must be 0 on average. So here is 0 of our residuals, unstandardized residual. Oh yeah, for the people that joined later, let me show again, because this is very important to know. If I take regression and I go to linear, so under save you tick those and you have standardized and unstandardized. You could use standardized. In the book they use standardized, but we don't, because it's a lot more difficult, and standardized means that they have been adjusted for the normal curve and the interpretation is different. So always click on standardized, both for predicted as well as for residuals. Okay, then we know that. So here's our unstandardized residual. And here's our H. And we want to see if the residual is on average 0. And I think it is, because here's our 0 line. And I think for every x, yeah, it's fairly okay, right? Yeah. Okay. Now, well, then we do the same for the other variable, but because I said you need to do, you take that out and you take education level in, do the same, and there it is. Also here, if you see this is 0 line, I think you're fairly above and below. Maybe 1 is very far above, here a bit more, but overall, the linearity assumption is all right. So linearity, I don't think is violated. Then we have the other Holmes-Geddes test. Sorry, I didn't get the name. And you can also check it with these graphs. Remember, homoscedasticity meant that the variance, so the dispersion of the residuals, is the same at every x. Here it's all quite close. Here it's a bit bigger. So towards bigger x's, the dispersion is a bit bigger. So there might or might not be a violation, but it won't be a big violation. And here's the same, because here it's close, here it's close. Here it gets a bit further away. So I would say there's also maybe a violation of homoscedasticity, so heteroscedasticity. Okay, but you can also, this is like, you can use this graphs if you were asked to already do the linearity. But if you were not asked to do the linearity, you first have to create those two graphs and then comment on both of them for the homoscedasticity. That's possible if you have 2 variables. But imagine you have 10. Then it's going to be a lot of work. And if you have to comment on all those graphs for linearity, you have no choice. But if you don't, there's another way to do it. Go to lazy dialogues again, you go to scatter and dot. You click simple scatter, define, and you want those, you want this one out. And instead of the x variables, you are going to put the unstandardized predicted value on the x-axis. To be honest, I'm not 100% sure why you do it. This is just how we learned it, and it wasn't also explained why you should do it. It's just we do it, as it is very often in this course, I must admit. But I think it's because the unstandardized residuals sort of depend upon the unstandardized predicted values, and in that way you can also see if heteroscedasticity is applied or homoscedasticity. But you don't need to know that. Only need to know that this is how you do it. Click on OK, and you get a graph. And this graph shows indeed that at bigger values of x, you get higher residuals, or sorry, at higher predicted values, you also get higher residuals a bit. So the bigger your predicted value, so for example, if your predicted value is 40,000, which is very high, your residual is also quite high. But here's also one outlier a bit. I think it's not really violated because here it's a bit smaller, bit larger, but I mean, if it would literally be like a cone, if it would go out like this, very much like a cone, then it would definitely be a violation. But now, I mean, it's probably doable. Yeah. So above, we concluded that there might be a violation of homoscedasticity. Thus, there might be heteroscedasticity. But here we say, yeah, there might be, but there's probably not. Okay? So indeed, the graphs seem to be a bit contradicting, because above we were more likely to conclude heteroscedasticity, but both show that there isn't a high chance of heteroscedasticity. Here. Okay, then we have to do the other two assumptions. Normality. Normality will be checked the same. So we went to graphs, legacy dialog. Oh, that's wrong. We go to graphs, legacy dialogs, histogram. Because normality always follows like sort of this histogram form, or it can be. And if you take display normal curve, then you can compare whether the residuals, so you want to see if the residuals are normally distributed, if they follow it well. So you put the residuals here, click on OK. And here you see, so those bars are your residuals, and this line is your normal curve. I think it follows it fairly well. There are some bigger values here, one outlier, a bit of an outlier here, but it follows it fairly well, I would say. Okay, and then the last assumption, independence, which we don't need to check because it's assumed that this is a random sample. So that's easy. And that are the 4 assumptions. If there are no questions, I'll give you 2 minutes to take it in, and then we continue. Okay, I hope you're. Oh, I see one comment. Oh yeah. Thank you. In what program are you? Are you in IBA or not? Okay, yeah, me too, but I know some are not. All right, we continue. It says, yeah, that's right. So remember the sum of squared errors is the same because it was just the actual y's minus the predicted values of y for all the y values and for all their predictions, and that's where the i's are for, and you square it. But of course, we never have to calculate that because we have SPSS, and that's what we call our SSE. But to obtain the sample variance of the estimated model, SE squared, we had that before. And then we had SSE, and we divided by n minus 2, if you remember. But now, and that's what I was hinting at before, now we don't have n minus 2. We have n minus k minus 1. And why do we have that? Well, in a simple linear regression model, you had two items, I would say. You had beta 0 and you had beta 1. And those make 2. So you divide by n minus 2. But in a bigger model, so in a multiple regression model, you get more variables or more items because variables are all the x's and you still also have the beta 0. So the k is the number of variables that you have. And the 1 stands for the beta 0. So in a simple regression model, you had k is 1 because you only had the one x variable, and then 1, so n minus 2. It's actually thus a special case of the multiple linear regression model. And now you can have, for example, if you have the variables age and education, you have 2 variables and you have the beta 0. So n minus k, which is 2, minus 1, so n minus 3, right? So that's where the k stands for, and that's why you can have n minus a bigger number than 2. That was what I was hinting at, because here, let me see, we had a degrees of freedom of only 147, and we had 150 observations. So we did minus 3 for the 2 variables and the 1 for the beta 0. So 150 minus 3 is 147. Then, yeah, the standard. So this is our variance. And of course, if you take the root of variance, you get the standard error, which is SE is root of the SE squared. Let me show you where they were again. So this is our sum of squares and residual is our SE squared, and this is our SE. I think it's also somewhere else. It was somewhere else, but I didn't remember. Well, this is good. Okay. So this is actually just repetition again. Basically, the multiple model is repetition of the simple, but with a few more variables. Then if we have the confidence interval, it's the same. Remember, this was our confidence. I'll make it a bit bigger. This was our confidence interval. So beta j plus minus this t alpha divided by 2 n minus k minus 1 times s by j. But you have for the confidence interval, or of course, like I said, you have this alpha, which you divide by 2. Why would you divide it by 2? Because you have it like confidence intervals always between 2 things, and what's left beside it must be equal on both sides. So if you have an alpha of 0.05, then at each side you must cut off 0.025. I think that makes sense. That's just 0.05 divided by 2. And your degrees of freedom, like I explained, isn't n minus 2, it's n minus k minus 1. Okay, and then your SB1 or your SBJ, because now we have this J because first remember we had B1 and SB1. That was because we only had one variable, and now we have multiple, so it can be any of those. So that's why there stands this J thing. And I included this for completion, but you never have to calculate this. You don't need to know this formula. You do need to know this one again. But it's actually the same formula as we discussed already, only with different degrees of freedom. Yeah, so the SBJ is this formula. But you don't need it because you can get it from your output. Let me show you. So your here, yeah, this is your B value. So that would be, if this is my x1, this is my x2, this would be my B2, and this would be my SB2. So that would be this one. And yeah, that's all you need to know. So again, there are 3 steps to do it. You write down this formula. That was step 1. Step 2 is you give the interval. And step 3 is you give the interpretation. I wrote this down in the previous slide set, but if I would include it again, it would just be too much repetition, and it's practically the same. And then step 3 would be the interpretation into two parts. Here we have hypothesis testing again. So it's actually the same. If I want to test if my age, if this is, for example, less than 0.5, right? That's a lower tilt test, one side lower tilt test. I could also test that it's different from 0. That would be a two-sided test with a hinge of 0. So that's actually the same. If you want to test one variable, so only age, leaving everything unchanged, you again use a t-test. Now just for completion, I've included them here. This is our critical value method. This is our p-value method. Let's go through them again quickly. First, you construct your null and alternative hypotheses. If you have an upper tilt test, then the H0 is the default hypothesis, so what you want to prove wrong, I would say, and your H1 is what you want to test. Sorry. So, for example, if I want to test my BJ is more than 5, then my H1 is BJ is more than 5, and my H0 would be my beta J is less than or equal to 5. Because remember, in the H0, we always include the stripe sign. Then in the lower tilt test, you do exactly the opposite, and in the two-sided test, you always have as the alternative hypothesis that beta J is unequal to something, and here you have that it's equal to something, for example, 0. Then you have your test statistic, which is exactly the same, except for your degrees of freedom, which is n minus k minus 1. And then you calculate the value of the test statistic, so you're the small t. So you fill in this formula, you get a number. And you reject or don't reject the null hypothesis. So if your critical value, that's your This is your critical value. And if your t is bigger than that, then you reject it. So your value, if it's bigger than your critical value for an upper till test, then you reject it. But if it's smaller than it for a lower till test, then you also reject it. Because remember, this was an upper till test, this was a lower till test. So you really have to look at what you're testing, and only then you can make conclusions. Because if the critical value is the value at which you may reject your null hypothesis. This value makes it so unlikely that it happens under null hypothesis that you may reject it. So if you get a value that's bigger than that critical value in an upper till test, you can reject it. And then the two-sided test is, for example, something is unequal to something, which means that if you get a value lower than a certain value, you can reject it. And if you get a value that's higher than a certain value, you can also reject the null hypothesis. But this actually is all repetition. And then in the fifth step, you draw the conclusion. For example, if your t is for lower, if your t is smaller, say your t is 0.5 and your critical value was 1, you say reject it because it's smaller, and we tentatively accept the alternative hypothesis. Okay, and then we have the p-value method. The first step is exactly the same. The second step is as well, and the third step is as well. Only the fourth step is different. Remember that the p-value is the value at which you it's really unlikely to happen. So the p-value, I would say, is the probability of obtaining an outcome as extreme as that. So for example, if the alpha is 0.05, which means that the outcome at that point is only has 5% of happening under the null hypothesis, and thus, if it happens, you can reject the null hypothesis because it's so unlikely to happen. And for example, if your p-value is 0.01 and you have a alpha of 0.05, then it's so unlikely to happen under the null hypothesis that you can reject it. And that's what you draw in the conclusion again. Okay, we are going to do an example. Suppose we want to test that growing older by 1 year increases your average wage by less than 0.50, holding education level fixed. All right, so what do we want to test? We want to know whether the beta of the wage is less than 0.50. And we can use a t-test because it's only about one variable holding education level fixed. So how are we going to do this? We can do this in SPSS, but first, we have to draw up the hypotheses. That's step 1. And I already said the alternative, so what you want to test, is your H1, and that's beta 1 less than 0.5. And the opposite is always your H0, which is beta 1 is more than or equal to, because remember, we always include the stripe in the null hypothesis. And that's this. So beta 1 is more than or equal to 0.5. Versus, you could say, and you could put a comma. I usually put versus here. And then the second step is your test statistic. And like I said, in your test statistic, you just throw in the formula, but you fill in the hinge. That's the small p. And that's 0.5 in this case. Then we're already at step 3. You go and calculate the value of your test statistic. How do you do this? We do this in Excel. So you go to your output. We already had that. And we wanted to test, do we want to test the age? Growing older by 1 year. Yeah, we want to test age. So you're going, you're going to copy this number, Ctrl copy, go to Excel, put an X, put it between brackets, and a minus 0.5, because that was our hinge. And you divide it by the way, if you click it a few times, you get it like this, and you can easily copy it because you get the entire number. You can also just copy this, but you are rounding in between because you have to round it to 3 decimals in the answer. So if you copy it like this, you might get, you know how to do it, but you might get just the wrong answer because you round it in between. So I recommend it to always click it a few times, Ctrl C, copy it, put it in here, and you get your answer. So this is our t value. Now we can calculate the critical value. How do we calculate the critical value? It was a lower tilde test. So you go to, with a 5% confidence level, I think, yeah. To is t.inf. You click it. The probability, which was 0.05, because remember, it always does it to the left side. So if I take 0.05, it's correct. If I take 0.95, I get the positive value, which is possible as well. But you have to take, then put a negative minus sign in front of it, because you are doing a lower tilde test. So it must be a negative value, comma, your degrees of freedom. Was that again? That was, scroll up, 147, sorry. 147. And you get your answer. So this is our critical value, and this was our answer. Let's see if that's correct. Yeah, that is correct. Yeah. Because, yeah, my answer is a bit different than this, but they rounded off in between and I did not. So the best is not to round off in between, because then you will always be correct. So what was our critical value was this. We had that as well. And our value of our t-statistic was this, which means that our t-statistic is smaller, or no, actually bigger, because it's negative, than our critical value. So it's not in the rejection region, because it's in the rejection region if it is smaller than this. If it would have been -2, it's not. It's this. So you do not reject it, because only at values that are smaller than this, those are so surprising under the H0 that you can reject the null hypothesis. But it's not, so you cannot reject it. Let's do it with the p-value method. Is t.dist. And we are asked for the x. And remember, that was this value. Dot the degrees of freedom, 147. And at the cumulative, you put the true. And you get an answer. And this is our p-value, which is very big. So you only have a confidence level of 65%. So there's 35% that you're wrong. Or your alpha must be 35% of being wrong to accept or to reject the null hypothesis. And that's obviously way too big. What was our alpha level? Our alpha level was 0.05. But our p-value is 0.3353. So that's obviously a lot bigger. So it's not surprising enough to reject H0. So you don't reject. And then you conclude, I would conclude, do not reject. Actually, this conclusion isn't entirely correct. I will write, no. Sorry. I will write the correct conclusion here. Okay, so this is the wrong conclusion because this is not how you're supposed to do it. So what should be the right conclusion? The right conclusion should be reject H0 since the p-value is bigger than alpha, or you can also say, of course, your critical value or your t value is bigger than critical value, because it's of course a lower tilde test is bigger than critical value, thus to not reject H0. Not enough evidence to conclude that growing older by 1 year increases wage bias than 0.50 on average. Always include the average because it's an estimation. Okay. Yeah, I don't know if you guys want to continue for a bit, because we also, of course, started later. For next time we have, how many slides are there? Yeah, 40 slides then for next time. I think that should definitely be doable. I don't think we can do the entire exam together then, but yeah. So if you want to maybe write in the chat, maybe we can work on for 10 minutes or a quarter. But if you have something else to do, then we will quit now. Okay. Okay, then we'll go on for just a quarter and then finish a bit more. So statistical significance. Like before, the most common hypothesis test for the multiple linear regression model is testing whether the regression coefficient is 0 or one of them or all of them. And that's what we call a statistical significant test. And it's quite easy because, like I said, if you go to the model, you can always find the t-value of a zero hinge here, and also the significance level, which both are low, as you can see. So probably they're both statistically significant because they're different from 0. That's what statistically significant means, as you can see, because you test beta j is different from 0 or it is 0. And if it's 0, then it doesn't help in the model, because if x goes up with 10, y won't change because of it, because the coefficient is 0. And if it's not 0, then y will change. So it's useless. So then it's useless in the model if it doesn't contribute to explaining y under H0, and under H1 it is useful. And if we reject H0, so we tentatively accept this one, then beta j is statistically different from 0. And we say it's individually statistically significant. Oh yeah. So we talked about R squared. R squared was the SSR over SST. And what did it say? It meant the variation that is explained by the model. So if it's 0.75, then a lot is explained by the model. And that's usually a good thing. You want it to be as high as possible. Now, again, you can see, here's this table, the ANOVA table. And here it's the same, SSR, SSE, SST, the same. Degrees of freedom, as I explained, this was the n minus k minus 1 for the residual. Here's the k and here's the n minus 1. You don't usually need them. They just completed it for sake. And the mean square, here's the SSR divided by k. You don't need that either usually. No, not really. And here's your error of the standard variance of the model, which was your SSE divided by this. We already discussed that, I think. And for a simple model, it was this was n minus 2. Okay. I also said that with the simple model, the coefficient of determination, also known as R squared, is the same as the sample correlation coefficient. You never need it, it's just a fun fact. But that's not true for multiple regression. It's only true for simple. So we can't use that anymore, in case you wanted to use it, which you don't. But there is one problem. So we said this was our ordinary R squared. So it was SSR divided by SST equals 1 minus SSE divided by SST, because of course SST equals SSR plus SSE. So if you rewrite it, you get the second thing. But there's a bit of a problem. The ordinary R squared measures the percent of variation in the Y data that is explained by the independent variables. But if you add more variables, so you go from 2x's to like 3, you add, so we have age and education on the influence of wage, but maybe country, nationality, gender, they might influence it as well. But maybe they don't. But if you add them, then the R squared will always go down. That's just, no, it goes up, sorry, it goes up. It acts as if more of the variation in the model is actually explained. And that's not always a good thing, because sometimes it's not true. Sometimes you add things that don't actually explain more of the variation. And that's where the adjusted R squared comes in. So the adjusted coefficient of determination. We call it R squared AJ, ADJ from adjusted. And that equals 1 minus SSE divided by n minus k minus 1 divided by SST divided by n minus 1. So this formula, you don't really need to know it, I think. No, but no, you don't need to know it because it's in SPSS, but it's obvious because the only thing that you change is you take this formula and you divide it by their degrees of freedom. If you look here, SSE has this degrees of freedom, SST has this degrees of freedom, and you divide it. So yeah, it's not very difficult. One thing, you don't actually use the adjusted R-squared, it's just included. If they directly ask for it, it is in your model here. Here is your R-square, and here is your adjusted R-squared. Yeah, you see it's lower, it's always lower, because this is always too high. But you don't usually use it, because you only use it for making a model, but it doesn't explain anything. So I made that red here because it's important. I slipped on this myself. If they ask for how much the variation in y is explained by the model, we use the normal R-squared, and you do not use the adjusted R-squared. It's just always given by default, okay? Yeah. Okay, this is again our ANOVA table. I have it here. Here's our real ANOVA table. And until thus far, we've only looked at until here. We looked at sum of squares, the degrees of freedom, and the mean square, which you don't really need. But there's more. We have an F and we have a sig, which stands for significance. And we can actually use those. Because thus far, we have only tested if one variable is useful in the model, or if one variable is more than 5, or less than 3, or unequal to 0. Okay? But maybe in a multiple regression model, we want to test if the entire model is useful. Because with the t-test, we could only use one. We could only test one variable for usefulness. Now we can test the entire model. How are we going to do this? We do it with the F ratio. And the F ratio tells us about the usefulness of the whole regression model. Okay, so that's easier said than done, of course. Here's an F-test. And an F-test is actually just sort of a t-test. It's only with more variables. So what you want to test is whether the whole model is useful or not. So your default or your null hypothesis is the following. Beta 1 is beta 2 is beta k. So for example, if there are 5, then your k will be 5, and everything in between is 0. And your alternative hypothesis is at least one of beta j is not 0. For j is 1 until k. So if k is 5, then you can also write, for example, beta 1 isn't 0 and or beta 2 isn't 0 and or beta 3 isn't 0 for all your betas. But if you have 10, then you will have some work. So how we write it down is the following. At least one of beta j is not 0. For j is 1 up until including k. You have to really study it a bit and just remember. And of course, under H0, the model is useless. Because if they're all 0, then it doesn't change when x changes. So we don't, the model really, it's useless. And if one of those, so under H1, at least one of them is not 0, then the model is useful. Because then y will change if one of the x's changes. Maybe all of them are useful, maybe only one. But the model is useful if at least one of them is useful. What is our F statistic? Remember we had our T statistic. And our F statistic is a bit different. And again, you really, really, really need to know this formula. So what's the formula? It's your SSR divided by K divided by SSE divided by N minus K minus 1. And of course your thing, your F with its degrees of freedoms. So your F statistic has two types of degrees of freedom. It has K degrees of freedom. So in the table, you see SSR has K degrees of freedom, and your SST has N minus 1, and your SSE, which we need, has N minus K minus 1. So you need to know those degrees of freedoms, or at least what they entail. If it's K, if it's 1 minus 1, or if it's, sorry, N minus 1, or if it's N minus K minus 1. Where were we? We were here. Okay, so if you know that, then you have this formula. And it has sort of 2 degrees of freedom because it has this K and it has this N minus K minus 1. And this is very, very important to remember. The F-test is always one-sided and upper-tiled. Remember that I said the t-test can be upper-tiled, it can be lower-tiled, or it can be t-tiled. The F-test can only be upper-tiled. We don't know why. It's just true. It is just true, and we assume it to be true. Okay, so here's the F-test. There are again the 5 steps. I am not going through all of them again, because we have done 2 times now. There are again 5 steps. First step is the hypothesis. Second step is the test statistic, so the one from the F. And again, you would only fill in the hinge, but there is no hinge here. So you just give the entire formula. That's why it's so important to know this formula. If they say, give the test statistic, it would be literally the easiest question you could get, because if you know this one, and you know that you should give this one and not a t or f partial or any other, you throw in this one and you're correct. You get just a point for free, I would say. And usually there comes in at least one of those questions. So yeah, know that. And then step 3, you calculate your F value as you would calculate your t. Same for null hypothesis p-value testing. And then you reject your H0 if your value of F is bigger than or equal to your critical value. And we will do the critical value in SPSS. I think there's an example. Yeah, we have an example. Okay, and the same for the p-value. You reject if the p-value is smaller than your critical value, which, smaller than your alpha level. And we'll do that in an example. And then you draw a conclusion. And it really is as simple as that. And it might seem very, very strange or very complicated at first, but it's actually not. It's just practicing. And I think after practicing enough, for me, that's quite a lot, I think. I don't understand things very fast, but if I can do it, you guys must be able to do it. So just practice, remember the steps, write them down for yourself or something, and you will get there. Okay, we will do one example, and then I think it's call it a quit, because like I'm just getting respect for our lectures, because I'm really, really getting a sore throat now. I've been talking for I think 4 hours, and it's not good for your voice. Okay, so let's do this example. As I said, you get the F value here. You don't have to calculate it yourself, you can. it takes time and it's probably going to go wrong. So that is why you can take it from here. And with the t-test, I said you can only take the, let me show you again. You can only take the t-value if your hinge is 0, right? With the f-test, you can just always, with the f-test, you can take it already from here, or you can take the significance. So this is your small f, the realization of f, and this is your p-value. Okay, let's have an example. Okay, we want to test whether the beta or the betas are 0 or not. So we want to test if the model is useful, and that's where we use the f-test for. Now we get the f statistic. So usually you do it with the steps. We have seen the steps a lot of times now, I think. So for this time, I included only the things you need to calculate. And but of course, if they ask, you always have to do the steps. Let's calculate the critical value and the p-value. You go to Excel. Here's Excel. And you do the is again, otherwise it's not going to work. And instead of the t, you take the f. And we had the inv van inverse. En you had the dist van distributie. And for the critical value, you always take the inv. And then it's going to say what you have to fill in. So you have to fill in a probability. I don't remember what it was. It was 0.95. So you have an alpha of, and since it's an upper till test, you just take the 0.95 because it's always to the left. So yeah, you need 0.95 and not 0.05, because then you would get a lower tilde test, and an f-test is always upper tilde. Then the degrees of freedom, we have to look that up. You have degrees of freedom 1 and you have degrees of freedom 2. Your degrees of freedom 1, is always your k. So your k. And your degrees of freedom 2 is your n minus k. And you need to remember that. So my k is in the ANOVA table here. And my n minus k is under residual. Let's look it up. So my k is 2. And my n minus k minus 1 is 147. So you type 2, 147. And you get a critical value of this. That's your critical value. Then what was our f statistic? It was this. Well, obviously that's a lot bigger. Thus, you can reject H0, and on the basis of this evidence, the model is useful. We can also do it with the significance. Here, that's very, very useful. It already gives you the significance. So you don't actually have to calculate it yourself. You can. I can try it. So you type is f dot dist, because that's what you use for p-values. It asks you for the x, which I think was 69 something. Degrees of freedom, which was 2. Second degrees of freedom, 147. And cumulative is true. Now you get 1. Yeah, that's because it's taking the reciprocal, but yeah, if it's, did I do it right? Yeah, I did do it right. Anyway, you see me doing it wrong, right? I get the wrong answer. And that's why I recommend you, if you can, just read it off your screen. You can go and calculate it yourself, but you might get it wrong. And SPS doesn't get it wrong, obviously. So you just get it from SPSS. And we see that the significance level is very, very small, which means that if the significance level is smaller than your alpha, which was 0.05, then you can reject H0. If you reject H0, you tentatively accept H1, the alternative hypothesis, and you conclude that the model is useful. Sorry. Okay, so yeah, I don't know what I did here. At this. Don't exactly know what I did wrong. Oh yeah, I know. It always calculates it, of course, to the left. So what I did wrong is I have to do 1 minus this, and then you get 0. Because it is such a large value that, let me draw it, because I might have confused you. If I draw it, so it goes like this. And then the value is like literally somewhere here. And like I said, in Excel, it always calculates this part. So now I get a confidence of an alpha of, or p-value of 1. And but I must have this small thing, because it's always an upper tilt test. So I have to do 1 minus that. And then I get 0. And yeah, I think that's enough for today. If you all agree, because we can easily finish. How many have we done? Yeah, we've done quite a lot today. We've done more than 50 slides. And then we need to do 30 next time. And the time that we have left, we can spend on an exam to practice. If that's okay with you guys. I will send you the slides immediately after this. And if you have any questions, you can ask them now. I will wait a few minutes here. Yeah, you can ask that as well. If you have any comments, if I can improve upon anything, because I do give a lot of tutoring, but never online. So like, I can't see if you don't understand. And usually, like if my bijleskinderen don't understand, I will see. And now I don't. Yeah, you guys, thank you very much for putting up with me and my Wi-Fi problems. I'm usually not like this, but anyways. It's how do you say it? It's like variable. I will say variable, but it's variable, right? Okay. Yeah. Yeah, I know. Yeah, I got like, I had an English teacher at my. I never had any English, and then I got a English teacher who was like literally English, and that's how I got the accent. And but he was also like Scottish, so some of my pronunciation is not correctly English. I know. It's really sad, but okay. I hope to see you guys on Wednesday. We start at 9 again, and then we will. Can you, by the way, hear me very well? Because I'm not wearing earplugs or anything, because they're broken.